filter. So let's say luckily you get an admission in a PhD and you join the lab and you join in an experimental lab. The very first thing your supervisor will say, if he is or she is working in electronics or anything close to that, they will say to make a filter, because filters are very much useful in any electronic circuit, and physics people really have to make these circuits in PhD. Although this is not a part of BSc and MSc syllabus, but in PhD, even when I was in IISc and I was joining, the very first task that I had was to make the filters. And we have to make a very good filters. And what is filter actually? Now, what happens is that when we are doing the physical studies, for example, I will give my example. I was working in graphene. So graphene is a two-dimensional material, and it has just one layer of atoms. And I was doing the electrical studies of graphene. So when I was doing the electrical study of graphene, I was sending some sine wave, so electrical wave, sine wave, and I was seeing basically the response of the graphene. What is the response graphene is giving me? Okay. Sometimes I was giving the DC voltage, and still I was looking at the response from the graphene. How is graphene responding to my signal? Is my signal remains as such, or there is any losses, or is there any gain? What is happening to my signal because of this graphene? Am I able to make a good transistor out of this graphene? So this was all my entire studies. When you are doing all of this study, sometimes your frequency range are very small, sometimes your frequency range are very large. Usually when you are in a low frequency range, you are in a physics. And when you are in a large frequency range, you are in a engineering. For example, 5G technology, 6G technology, 7G technology. This is high frequency signals. You need a very high frequency receptors, you need a very high frequency receivers and all of that. So you are in an engineering background. You are in an engineering problem. But when you are in a low signal or a low frequency signal, means the frequencies are not that large, then you are sort of in a natural frequency phenomena. You are basically observing natural frequencies. The frequencies which are coming from the lattice vibrations, or the frequencies which are coming from the interactions of the particles. And those frequencies, all of these problems comes under the physics. So for physics student, the filters is very important, because we deal with the low frequencies to the medium frequencies. Okay. And the problem which happens is that since we are dealing with the natural frequencies, the background noise also have the similar frequency. And that is a problem for us, because the background also has a similar frequency. So let's say in a background, I am hearing 10 hertz of frequency. Let's say, I'm just taking an example. So let's say in the background, I'm hearing 10 hertz of frequency. Let's say I want to study 20 hertz of frequency from my system. So my system is giving 20 hertz of frequency. Now the problem is that this 10 and this 20 will interfere with each other. And I have a very big problem, because I want to study my 20 hertz frequency. But the problem is that in the background 10 is also there. So I'm getting both the signals and I'm getting confused, because they both are getting mixed up and I am not getting something which I want. And that's a problem. So I want to stop this 10. I don't want this 10 to be observant. So what I do is I use a filter. Now, what does this filter do is that it will block all the frequencies less than 20 or less than 15. So it will block all the frequencies which are less than 15, and only those frequencies will come to you which are more than 15. How does it work? So let's say you have a person, and this person, you are instructing this person very clearly. Okay, if the frequency less than 15 comes, you don't do anything. Just don't do anything. Let it pass. But if the frequency more than 20 comes, you gain it, you increase its power. So what happens is that for all the frequencies which are greater than 15 will get amplified, and all the frequencies which are less than 15 will not get amplified. So you can see your 20 hertz frequency very clearly, because that is amplified, but the 10 hertz frequency is not amplified. So this is known as the high pass filter means let the high frequency pass and low frequency block. So I am letting frequency more than 15 amplified, but frequency less than 15 not amplified. So this is known as high pass filter. High pass filter means if I have a cutoff frequency 15, so any frequency more than 15 will pass, means it will get amplified. But any frequency less than 15 will not pass, or you can say it will not get amplified, so you will not see as much. Similarly, on the other hand, we also have a reverse kind of situation. Now, sometimes what happens is that the frequencies are larger, the background frequencies are large sometimes. So let's say they are kilohertz, 10 kilohertz. And the problem is that you don't want that frequencies in your data. You don't want, okay, you have 20 hertz frequency and also you have 10 kilohertz frequency. So you're seeing both of them. So you're getting confused that if is this 10 kilohertz is getting from my system or from the noise. So you don't want that high frequencies. You only want your 20. So you block the high frequencies. So you say that anything which is more than 500 should not come. So anything which is lesser than 500 should come, and anything which is greater than 500 should not come. That is known as low pass filter. So if I have a frequency, let's say 500, set up frequency 500. So anything less than 500 will be visible, but anything more than 500 will not be visible. So low pass filter. So both the filters are useful, high pass filter and low pass filter. The only difference between them is that for high pass filter, it will allow high frequencies. So let's say what higher than cutoff. So let's say your cutoff is 10. So anything more than 10 will pass. So this is high pass filter. And what is low pass filter? Let's say your cutoff is 500. So anything lower than 500 will pass and more than that will not pass. So both the circuits are important. So I will put both the filters in my circuit. So I will say my frequency should be between 10 to 500. I only want to see the frequency between 10 to 500. So for 10, I will use high pass filter, that it should be more than 10, higher than 10 I want. So I need high pass filter for 10. And I need low pass filter for 500 because I want everything lower than 500. So high pass filter for 10 and low pass filter for 500. I want between them. That is what I do. Now there are different ways of making the filters. Before I go into that, any doubts still here? Is it clear? What is filters basically, and why do we use them? Yeah? Any doubt here? Is it clear? Yeah. What do you say? Is it okay, everyone? Should I repeat? What do you want? Is it okay or not? But let me know.
Just want to confirm one thing कि
Yeah.
अगर हमें कोई बैंड को पास कराना है तो हमें दोनों फिल्टर्स का यूज करना पड़ेगा, राइट? लो पास फिल्टर एंड हाई पास फिल्टर.
Yes, because otherwise you want band means that starting and ending both limits are there, right?
Yes.
Yes. So you need both filters. We will do that question. Actually, CSN had asked that question. Okay, good. Okay, now second thing, how to make these filters. So in electronics, there are two types of circuits or two type of elements. One of them are known as the passive elements, and one of the known as the active elements. Now there is a very clear difference between both. Passive elements basically means the elements we don't need any power to work. For example, if you have a resistor will work. You don't need any power to use it. But active elements means transistor, OPAMP. So these are some. I don't know if you have ever seen an OPAMP or a transistor, but you cannot use an OPAMP or a transistor without any external supply. So if you have a transistor like this, so this is your power supply. So you use power supply, and this is your input voltage. Okay, so you need power to use transistor. Transistor will not uh, be useful until unless you apply the power to it. And then once you apply the power, then the transistor will start working. Similarly with OPAMP. So these are known as the active elements. So the elements of the electronic circuit which needs power to work are known as the active elements. But on the other hand, the elements which do not need, for example, resistor, capacitor, inductor, these are all the things that you have studied in your lower classes. Resistor, capacitor, inductor. Capacitor is a capacitor. You don't need any power to use it. Now don't confuse it. Okay, without power, there is a difference between input and power. There is a difference between input and power. What is the difference? For example, let's say I have a resistor and I apply it to the battery. So this is my input. This is not my power. So if I apply my input, my resistor will work. I don't need any external power to use it. Okay, no. You have applied the input, but also you need a power to use it. No. But in the case of transistor, this is my input, but I also need power to use my transistor. Otherwise, my transistor will not work. It will not amplify, because otherwise energy conservation will be a problem. Energy conservation. Transistor can be used as an amplifier. Transistor is not an amplifier. Transistor can be used as an amplifier. Transistor has other functions as well, right? Okay, so okay. Now, why? Because if you want to amplify something, you want to increase the signal strength, it will not happen automatically. So let's say you give 2 volt and it becomes 5 volt. Don't you think energy conservation is in crisis, right? So if there is some element which can automatically convert 2 into 5, then it's an energy problem crisis, right? How do you conserve energy? So the answer is that don't get so excited. There is a power which is connected to amplifier. So that power is increasing 2 to 5. So this OPAMP is only doing what? This OPAMP is basically taking the power from the power supply and increasing the input. So input is 2. This OPAMP will make it 5. Why? How it will make 5? Because this OPAMP is taking the power from the power supply. But resistor does not do anything like that. Resistor just can reduce the power but cannot increase the power. If you have 2 volt, resistor cannot make it 5 volt. Yes, energy losses can happen, but energy increase cannot happen. That is why there are some passive elements and there are some active elements. Today we will learn how to do the filtering using the active elements. And to be very honest, if you are very good in making the filters, I think you are in one of the top of the physics field, because many less physics people know diode is active or passive. Diode is active or passive. Diode is also passive. Diode is also passive. So diode is 110% passive, right? Okay. So let's learn, right? So trust me, if any one of you joined the PhD, today's lecture you will always remember. You will thank me very later if you join the PhD. There is no person in this moment who don't need this in PhD. If you join theoretical, that's a separate issue. Okay. Now, let's start studying low band pass filter. So low band pass filter means this is my cutoff. Anything less than that, let it pass. But anything more than that, don't let it pass. So low band pass filter, low band. Low means let lower frequencies pass, but higher frequencies block. And the transfer function, or you can say the characteristics, are shown here. You can see that this is my cutoff frequency, and anything less than that has a very high gain. Gain means the voltage increases, but anything more than that has a lesser gain or decreasing gain. So what will happen? So let's say there are many frequencies coming, and I have a low pass filter which is 15 hertz or 500 hertz, let's say 500 hertz. Now, frequencies which are less than 500 will get amplified, because for them the gain is very large. So 500, any frequency less than 500 will increase, means their voltage will increase or their amplitude will increase. But any frequencies greater than 500, they will not increase, they will remain as such. So in a final data, you will see lower frequencies much more. You will see high peaks for the low frequencies. Okay, so this is what will happen, and circuit will amplify the frequencies which are less than the cutoff frequency. So low pass filter means the frequency is lesser or smaller than the cutoff will pass. The frequencies which are lower than the cutoff will pass. That is why it is known as low pass filter. Okay. So circuit allows frequency to pass which have a frequency less than the cutoff frequency. You don't have to go in too much detail. You should know that this is how the circuit looks like. Okay. For a physics student, this much is enough. This is a circuit. So this is your OPAMP, and this is your feedback circuit. So you have two feedback circuits, R1 and RF, two resistors you use, and here is your grounding. Okay. And this is your output voltage, this is your input voltage, this is again your grounding, this is resistor, and here is a capacitor. In this entire circuit, rest everything is just for the formality purposes, or you can say to increase the efficiency purposes. The main element is this one. This is the main element, and this RC circuit is actually doing filtering. This RC circuit is responsible for filtering. So if you ever see a circuit like this, where you have a resistor, input, then resistor, then capacitor, and then output, you understand that this is a low pass filter. It does not matter if it is connected to a transistor, it does not matter if it is connected to an op-amp, or it does not matter if it is individually behaving. This thing is a low pass filter. Wherever you see some structure like this, you understand that this is a low pass filter. Okay, and this is something you have to do. Now, what is the cutoff frequency for this? The cutoff frequency can be calculated by using 1 by 2 pi RC. This is a formula. I'm not giving you the proof because then we will completely shift to a very new territory. Then there are 7 or 8 lectures which are completely lined up. Okay, so I'm just giving you what is required. If the question comes beyond this, it can come beyond this. I'm not saying that it cannot. But if we start digging into this, then it's a complete lecture. Because I remember during my PhD time, I watched at least one complete lecture series for filters only. And this is a very new territory. So don't enter into it. Whatever CSNet is asking, we will just do that. So cutoff frequency is given by 1 by 2 pi RC. Something I want to give you as a feeling that why is this acting as a low pass filter? Because you should have a feeling that, okay, because this question can be asked in an interview. So you should have a feeling that why is this happening? So let me draw my circuit here. So I have one resistor, I have one capacitor, and I have input voltage, and this is my output voltage. Okay. So what is the resistance of a capacitor? And yesterday we talked about this. The resistor of the capacitor is 1 by omega C or 1 by 2 pi FC. If the frequency is low, means the frequency is low. If the frequency is low, then the resistance of the capacitor is very large. So resistor does not like passing the lower frequencies. So the capacitor hates it. Capacitor don't like low frequencies. It does not allow low frequencies to pass. Because if the frequencies are low, the resistance of the capacitor is very high. So what will happen? So let's say the low frequency signal is coming. So low frequency signal is coming. Capacitor will say, no, 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 no. I will not let you pass through me. I will not let you pass through me. So what will happen? It will pass to the output. It will pass to the output. So you will get a low frequency signal in the output. So you are sitting. So I am at input. You are at output. So I am at input. You are at output, and I send you a low frequency. This low frequency will come, and come till here, and then this low frequency will ask the capacitor, "Can I pass through you?" So the capacitor will say, "No, I don't like low frequencies because I have a very high resistance for low frequencies." So this low frequency will not go to the capacitor, and it will directly go to output, and you will receive my low frequency. So in the output, I am getting low frequencies. But if the frequency is very large, if the frequency is very large, then the capacitor has no problem, because then the resistance of the capacitor is small. Yeah, J term is missing. That is for a phase. So we are not interested in phase. That is why I did not write it. Okay. J is written only when the phases are important. So okay. So now again the frequency is large. So capacitor will say, okay, no problem. Now the frequency is large. I have no resistance for you. Means no means very less resistance for you. So you can pass through me. So now I send a high frequency. This high frequency will reach till here, and then again it will ask the capacitor, can I pass through you? So the capacitor will say yes, come through me. So all the high frequency will pass through the capacitor and very less high frequency will reach output. So you are not receiving my high frequency because my high frequency actually goes to the capacitor, but you are receiving my low frequency because my low frequency does not goes to the capacitor. So that is why in ultimately in an output, what are we getting? We are getting low frequencies and we are not getting high frequencies. That is why this is known as a low pass filter. Is it clear? Is my point clear to all of you? What do you say?
So,
Any doubt, please? Yeah. Is it
I mean,
clear? Yeah.
I am a
Yeah.
bit
Please.
confused about like the circuit looks a bit incomplete, right? Like about which are
No,
we
no,
measuring the output?
no. We are not measuring the output. See, this circuit is attached here. So whatever will come here, only that part will amplify, right? So let me show you here. So there's a little bit lag. So whatever will come till here, only that part will get amplified, right? Otherwise, we have to reach to the OPAMP. Only then OPAMP will amplify it. So before an output, there is an OPAMP. So whatever reaches here, that will get amplified, and finally, this here it will be amplified. And whatever does not here will not get amplified, and that will reach without amplification. What do you say? Is it clear?
Okay, okay.
Yeah, right. So that is why I only focused on this part of the circuit, because if someone reaches here, then it will get off, because op-amp will amplify it. Okay. Okay. Yeah. Any other doubts, please? Any conceptual problem anyone have? Okay. So very important circuit for you. Don't take it lightly. You will need this in your life if you want to be in a physics career. Yeah. Okay. Similarly, we have a high band pass filter. What is high band pass filter? So I have a cutoff frequency. High band pass filter says that whatever is more than that, let it pass, and whatever is less than that, don't let it pass. Okay. And unfortunately, I made the same circuit. Sorry for my mistake. I think there will be little bit change here. Let me check my notes. A second.
R and C will be switched. Right?
Yeah, it should be switched. Yeah, that. The only difference between low pass and high pass is the rest entire circuit is same. The capacitor will be replaced by a resistor, and resistor will be replaced by a capacitor. And this becomes your high pass filter. Okay. So how is this high pass now? So let's say I send a low frequency, and immediately in front of me there is a capacitor. Immediately in front of it. First, in before what was there, after some time there was an option that I can go to a capacitor or I cannot go to a capacitor. But now there is no option. I have to pass through the capacitor anyway. So there is a capacitor directly in front of me and I send low frequency. This capacitor will say, no, I don't allow low frequency. So low frequency will never reach. But I send high frequency, this capacitor will say, okay, let it pass. So that is the difference. That is why these things act like the high pass, because I have to pass through capacitor. I cannot prevent capacitor. In the previous case, the capacitor was at the turn. I can go further and then I have an option. I can go to the capacitor or I cannot go to the capacitor. But now I don't have an option. I have to pass through capacitor. And only high frequencies can pass through capacitor. So that is why this circuit will only allow higher frequencies to pass. So if the frequency is less than cutoff frequency, it is blocked, and if the frequency is greater than higher frequency, it will pass. Okay, so this is your circuit for high pass, and again the cutoff frequency is same. Okay. Okay, now I want you to look at this circuit and tell me, is it high pass or low pass? First one, just look at it and tell me.
High pass.
First one is a high pass, and what about the second one?
Low pass.
Low pass.
So initially we have a high pass and then we have a low pass. So a very difficult looking circuit, but now it's easy because you know, by looking at it, you know that this is filters. It's a high pass and low pass filters. And just directly by looking at the question, you can say, and now you can read the question. So they say that in a circuit diagram of a band pass filter, the resistance is 10 kilo ohm. Okay, 10 kilo ohm. And in order to get a lower cutoff frequency, 150. So you don't want anything lower than 150. And then upper cutoff frequency 110 kilohertz, and you don't want anything above 10 kilohertz. So you don't want anything lesser than 150, and you don't want anything more than 10 kilohertz. So you want everything in between this. So they said, what is the choice of your C1 and what is the choice of your C2? So the first one is high pass filter. So high pass filter means the frequency above this should pass. So above what? Above what? Above 150 should pass. So I need my cutoff frequency to be 150. So then I will use my formula Fc equals to 1 by 2 pi RC1. And then I can take my C1 there and frequency downwards. I can write 2 pi. R is 10 kilo ohm. So 10 kilo means 10 to power 4. I put my value and C1, F is 150 hertz. If I do little bit of mathematics, I will get 0.1 microfarad, which is my answer. So my C1 should be 0.1 microfarad. Similarly, on the other hand, I need low pass filter. Lower than that. Lower than what? Lower than 10 kilohertz. I want everything lower than 10 kilohertz. So then again, I will use my formula of frequency 1 by 2 pi R C2, and C2 from here comes out to be 1 by 2 pi R frequency. Frequency is 10 to the power 4, and if you solve that, that will be 1.5 nanofarad. So this is usually what happens, and this is your question, and this is your answer. Yeah. Any doubts still in this question? There is one more question which I have not covered in this class, because you do that. There will be at least 2 questions in a quiz which are based on these filter circuits. So you go for those questions and you try that after this lecture, and now you will be able to solve that question. I think Sahin asked 1 or 2 days ago that how to solve such problems, right? So this is how you solve it. Okay. Okay. Now, very interesting question here I have. So if you go with these numbers, and this is not something I will discuss today in the class, this is just for you to think and give me an answer in a group if you get an answer. Okay. And let's say this is let's say I'm your supervisor and you come to me with these numbers. So you come to me with the saying okay, it's 0.1 microfarad and 1.5 nanofarad, and you come and say that, okay sir, we need the capacitors of this amount. And I very straightforward, I say that, okay, I don't have nanofarad capacitor, because in the market it's not easily available. I have picofarad or I have a microfarad. Nanofarad is not there. Now what will you do? Okay, as a supervisor, your supervisor says that I have a picofarad and a microfarad. Now what will you do? Okay, so you change whatever you want to change in this circuit. Okay, and you make a circuit. Okay, the results are still same. I still want the same frequencies, but somehow your supervisor says that I have only picofarad and microfarad. How will you solve this problem in your PhD? Okay, so this is a challenge question. You can think of it. Nothing very difficult here. You can do that. Okay. Yes, then you have to think of the consequences also. Okay, that is what I want. That is series and parallel always allowed, or is there any consequences of doing series and parallel? And you have to think of the consequences. Okay, yeah. Because how do you make a series? Let me give you a very clear consequence. The condition in this case is that you want to work at a low temperature. Let's say you want to work at 1 to 4 Kelvin, or let's say millikelvin. People are very easily working in millikelvin. I was working in nanokelvin, so not a problem. So people are working in millikelvin, nanokelvin, and your supervisor just says that if you want to do series and parallel, how will you weld them together? How will you do the soldering? And will the soldering bring any new resistance? So if yes, how much? And will this soldering be able to hold that much of temperature difference, going to millikelvin, come back to the room temperature, going again to millikelvin, again come back to room temperature, and sometimes heating also? So the question is very clear here. The question says that your supervisor tells you that you don't have a nanofarad of capacitor. You have either microfarad or you have a picofarad. What will you do to solve your PhD problem? You have to do something. And if you do series parallel, the problem you will face is that when you connect in the series parallel, you need to do soldering, and that soldering can be a problem. Okay? If you have some technical event which can prevent this soldering, then it's a better solution. So think of it. Okay. Next, let's go for the next topic. The next topic is current to voltage conversion. Many times we have a current circuit. We have a current and we want to convert it into the voltage. And we have to do it in a technical way. Sorry, yeah. How you can convert a current into voltage? Basically, current source into voltage. If you ask this question to a class 12th student, he has a very simple answer. He will say, well, okay, you have a current source, you have 2 ampere current, okay, pass it through resistor. So your current will now pass through the resistor. So there will be a voltage across this resistor. How much voltage will be there across a resistor? V equals to IR. And you use this voltage. So it's very simple. You converted your current into voltage. This is what your class 12 student will tell you. Can you tell me that what is wrong with this? I have a current. That current passed through the resistor, and that there is a voltage across this resistor, and I use that voltage. Simple. Current converted to voltage. Can you tell me what is wrong in this entire story?
Energy loss as heat.
Energy loss, I won't say. Energy loss, voltage will remain voltage, right? Why there will be energy loss in this case? We have a source.
I square RT, right? Heat.
No. So people usually misunderstood energy loss, especially physics people I have seen, they misunderstood energy loss. You have a battery, right? So always 2 ampere current will pass and always 2 ampere current will come back. So 2 ampere current is not going to change. And you don't care about the energy crisis. You have a lot of electricity, so don't think about that. Don't have to prevent energy losses. You just have to make sure that voltage remain fixed. Is it possible in this case? What is the problem in this story? Why I cannot convert my current into voltage like this? I should be able to. Why I'm not able to do that? No, dissipation through wires. What's the problem with that? So let's say 50% of energy is lost. So what happens? Resistance will change as it sits. No, it does not change. Go and buy the resistors from the. I will give you 10 links for buying the resistors. They will not heat up whatever you do. So don't. That's a technological problem. I'm asking you as a physics student. Don't think of a technical problems. Think of it as a conceptual problem. What's a conceptual problem here?
When we connect something to this potential difference V, then it will change.
It will change. Yes, perfect. So when you try to use this, so let's say I try to use this. So this was my circuit before. And now I say, okay, let's use it. So I put my resistor. So use it means, let's say I connect a bulb. So when in electronics, you represent everything with a resistance. So bulb is a resistance, fan is a resistance, AC is a resistance, and this is known as a load resistance, right? Load resistance. So let's say I try to use this. So I connect my bulb here. Now the problem is that the current I was coming. So now not the entire current I will go here. Some current will go here and some current will come to me, to bulb. So the voltage of this thing will change. This voltage will not remain IR. This voltage will become I1R, because the now not all the current is going through this. So the voltage across this will change, and it will change according to load. So if the load is very large, then most of the current will go from here. If the load is very small, then some very less current will go from here, and most of the current will go from load. This is not a reliable voltage source. So if you connect a small resistance, voltage will be large. If you connect a large resistance, if you connect a small resistance, voltage will be small. If you connect a large resistance, the voltage will be going to be larger. So the voltage source depends upon the what you are putting. And this is not you want. This is, you want that if you go and buy the voltage source from the market, it should always give you 9 volt or 10 volt or 20 volt. It should not depend upon what you are putting in. If you are using a bulb, it gives a different voltage. If you use a AC, it gives a different voltage. So that everything will change. Then you don't know that every time you have to check that what voltage it is giving. And this happens because now not all the current is going to this. Some current is also going to the load. And that is one of the conceptual problem which you cannot avoid. You cannot avoid this problem. This is not a technological problem. This is a conceptual physics problem. Okay, and you cannot avoid this. Load will always have some resistance. There is no load in this world which do not have any resistance. But ideally, you want load to have a very large resistance, very, very large. Because if the load resistance will be very, very large, then almost no current will pass through this. And again, the entire current will pass from here. Then you are again back to what you started. Previous case, when all the current was passing through the resistor. So ideally, you want your load to be very large, so that if load is very large, no current will pass through the load and everything will pass from here. And this is what you want. Then the voltage will again be IR. But if some current also passes from here, then the current voltage will become I1R, and that is small voltage. So this is a conceptual problem, and in order to solve that, we take a benefit of a OPAMP. We use OPAMPs or active circuits to convert current into voltage. Okay, and this is not something we do a lot in physics labs, because we usually buy voltage sources and we don't care to open it. But if you open it up, you will find that there are active current to voltage converters. Okay. Okay, so how does your voltage source looks like, or current to voltage looks like conversion? So you have a feedback resistance. You have other terminal, which is non-inverting terminal, grounded, and you have this input current. Okay, so now you know from the virtual ground. So if the voltage at this point is 0, then the voltage at this point is also 0. So both the points have the same voltage. Yesterday we discussed about this. The input voltages has to have the same voltage. So if this is at 0, then this is also 0. So whatever input current comes, the entire current goes to feedback, because current can never enter the OPAMP. So whatever current comes from input, the same current goes to feedback. So current in input and current in feedback is same. What is current in input? That is given by us. The current in input is I input. And what is current in feedback? Current in feedback is voltage difference divided by resistance. What is the voltage difference? Voltage here is 0. Voltage here is V output. So the voltage difference is 0 minus V output. So the voltage difference is 0 minus V output divided by resistance, which is RF. So what is your V output? Your V output is minus RF into I in. So you see in output, you are getting a voltage. And in no case it depends upon a load. You see, it only depends upon the two things. One is RF and one is IN. IN is your source and RF is your feedback. So it does not depend upon the load. So voltage will remain same for all the loads. You use a bulb, you use a light, you use a fan, or whatever you use, the voltage will be same. So that is how you convert your current to voltage. Is it clear or any doubts? Is it clear, everyone? What do you say? This is asked in one way or other in CSIR net exam, and it can be asked. So you should know this. This is the benefits of having a active filter, mean circuits. Okay. So I hope it is clear. Any doubts if you have, please let me know. Don't keep any doubts with you. You can easily ask the doubt in your chat box. Okay. Or you can unmute yourself as well. Yeah. Okay. Now I will end the session with discussing 4 circuits, and then we will close the session. And four circuits, and which is very important. And these 4 circuits will be very much used in your quiz questions. So when we will go and do the quiz questions, you will need these questions. You will need the circuits. First is integrator. And did I discuss this in the integrated? Did I discuss in the 2 lectures which I shared with you? I think I should have done that, right? I must have done that. Did I discuss integrators in those 2 lectures?
No, sir.
No.
No.
Okay. Okay. Let's. Okay. It's not possible, but no. I'm talking about the 2 lectures I gave as a homework. Okay. ठीक है. No problem. Let's do an integrator. So what is integrate? So in physics, this is very important. You need to integrate the circuits, integrate the signals.
Yes, sir. Yes,
So
sir.
let's
You
say you
did
have.
it, sir.
Yeah. So let's
Yeah.
very quickly go through it.
Yeah.
So yeah, if you want to integrate it, so let's say someone asks you that how calculator is integrating the things, how your computer integrates. So if you give some function to your computer and it integrates, how does it do? An integrator is one of the best way to convert cos into sine, sine into cos signals. And integrator can also be used to convert linear straight signals into linear signals, right? So square signals into, or you can say rectangular pulse into triangular pulse. All of these things are used by or done by integrator differentiator. So what is integrator? So you have this non-inverting terminal grounded, you have this input signal which is Y, you have this resistor, and you have this circuit C. So input current is coming in and output current is going on, and so here there is a feedback current. So this circuit will behave like a integrator. I will not go into mathematics of it, but because that I have already discussed. But if you ever look circuit like this, you should know that this is an integrator circuit. Okay. So whatever current is coming from here, the same current will flow here because no current can pass through the OPAMP. And if the voltage here is 0, then the voltage here should also be 0 because both the terminals should be at the same voltage. Now we talk about it. So what is the current here? So current in this branch is the voltage difference. What is the voltage difference? Y minus 0. If V1 and V2 is 0, how can OPAMP amplify the signal? I do not get you. I don't get you. If V1 and V2, which V1 and V2? So you're saying that these 2 points are if 0, 0, then how can it amplify? It is not amplified. Nothing is being amplified here, right? It's acting as an integrator. It's just integrating the circuit, and it will add some gain into it. Okay. So it does not mean that no current is entering it. It means that so if you look at inside the OPAMP, there is a transistors, and there are 2 transistors, differential transistors. So one transistor is on this side, one is on this side, and then there is a entire theory actually. But your question is very good. That if from the outside, if you look, then there is no voltage difference we have given, but we have given it. On the other transistor, it goes. Okay. Anyway, we will talk about it someday. So let's say there is a voltage okay, input current is coming and it will go straight to here. It will go straight to here. So what is the current in this? voltage difference. Voltage difference is Y minus 0 by resistors. By resistors is R. And what is the voltage here? Or what is the current here? The current here is given by, I don't know. So I write the current as dq by dt. And in capacitor, Q can be written as CV and C can be taken as common, and then you get dV by dt. Why I put a negative sign here? Because you see voltage difference is actually 0 minus V output. So you are basically doing the differentiation of that. So you get dV output by dt. So dV output by dt. So then you integrate both sides with time. So you basically get V output as minus 1 by RC integration of Y dt. So you see, you are basically integrating your input signal. You basically integrating your input signal. Okay. Similarly, if I reverse the situation, I put a capacitor on the input side and I put a resistor on the feedback side, then this thing will become a differentiator. So then your final result will be V output is equals to minus RC dy by dt. So in that case, your circuit will start differentiating your input signal. So whenever you see such circuit, a BSc student might have to think. If you're a BSc student, then you might need 1 or 2 minutes to imagine that, okay, what will happen in a circuit. You will do this small mathematics. But if you're an MS student, I don't think this should happen. If you see such circuit, your brain should say, oh, this is a differentiator. If you see a circuit, you should say, okay, it's a high pass filter. Oh, it's a low pass filter. Oh, it's an integrator. It's a differentiator. So this should happen like that. So you should see these circuits. So make a list of the circuit, make a page of the circuits and put it in your table and every day look at these circuits. Because ultimately it should be in your head sometime. Okay, this is my circuits. And if you have that kind of ability, you will go very, very up in your field in PhD. Usually people, because when the supervisors, I have seen physics people trembling actually. So whenever we had an new interns coming for an interview for an internship or something like that, they used to tremble when we asked them what is differentiator, what is integrator. So they used to take a time. And when you are doing a derivation in front of a teacher, anyway you are in a pressure. And so if you already know the answers, then it becomes much easier. If you already know that yes, it is going to be an integrator, then you can put, you are in a much better way. So please do that. It will help you. Okay. Especially if you are willing to come to institutions like IISc or something like that. Okay. Yeah. Then there is a logarithmic circuit. This is something new. You might have seen it first time, or some of you might have already seen. If you look at a circuit like this, instead of C, I use a diode. Nothing else. Instead of C, I use a diode. Then my output will be the log of input. So whatever is my input, my output is a log of that. So in your circuits, if you want to do log, then you use this circuit. And if you do want to do anti-log is also sometimes known as exponential. This is also known as anti-logarithmic circuit, or sometimes also known as the exponential circuit. In that case, nothing you have to do. You just have to switch diode and resistor. So if you switch diode and resistor, you will get an anti-log. So whatever is your input, you will get an anti-log of that. Okay? So that is known as the EY. Now I have one question for you before I end this class. What will change if I reverse the polarity of this diode? My diode is something like this. Let's say I attach my diode in the reverse. In this also, I change the polarity of my diode. I make N side on this and P side on the other side. What will happen to my circuit? Will it still be log and anti-log, or will it not be log and anti-log, or will it be minus log? And what will happen? It will be a phase change, it will be a function change, it will be a gain change. What will happen? Okay, and think about it. Think of this question. Okay, and go for it. So this is the circuits you need. Tomorrow we have a discussion class. So we will meet tomorrow now 7 p.m. and at least 2 hours it will take. So for 2 hours I will be discussing the 20 questions of OPAMP and the filters. Sorry, Fourier transform of some of the circuits. Now you have any doubts, please ask me. Okay, so that's the end of the lecture at this moment.